Today our topic is about arrays. What do you mean by arrays? Arrays are the most common and important composite data types dating from Fortran. Unlike records which group related fields of disparate types, arrays are usually homogeneous. Semantically, they can be thought of as a mapping from an index type to a component or element type. So it is a mapping from index type to element type. Next we look what are the array requirements. Most languages require that index be discrete. So some languages such as Fortran require it to be an integer. Some scripting languages even allow non-discrete types. With a non-discrete need some kind of mapping such as a hash table to get into the actual array. Generally, the element type can be anything, although some require to be a scalar. Next we look what is a slice or section in an array. A slice or section is a rectangular portion of an array. We can see it in figure on next slide. So this the shaded portion is the slice in an array. Much like the values in the header of an enumeration control loop, A, B, C in a subscript indicates positions A plus C, A plus 2C through B. If A or B is omitted, the corresponding bound of the array is assumed. If C is omitted, 1 is assumed. It is even possible to use negative values of C in order to select positions in reverse order. The slashes in the second subscript of the lower 8 right example delimit an explicit list of positions. Next we can see how an array is declared. In C it can be declared as character up then square bracket we can give the size 26 like that. In Pascal the example is variable upper array A to Z of character. In Fortran it is character dimension 126 upper character 26 upper shorthand. Like this in different languages array is declared. Note that in C we start counting at 0 but this is not true in Fortran. Next we look dimensions, bounds and allocations. What do you mean by global lifetime, static shape? If the shape of an array is known at compile time and if the array can exist throughout the execution of the program, then the compiler can allocate space for the array in static global memory. Then what is local lifetime and static shape? If the shape of the array is known at compile time but the array should not exist throughout the execution of the program, then space can be allocated in the subroutine stack frame at runtime. So this is mean by static shape in local lifetime. So static shape in global lifetime and is there static shape in local lifetime. Then local lifetime shape bound at elaboration time. So this is elaboration time allocation of arrays in ADA or C1999 is shown. Here M is a square two-dimensional array whose bounds are determined by a parameter passed to foo at runtime. The foo is the program you can see at left side of the figure. The compiler arranges for a pointer to M. Okay, the compiler arranges for a pointer to M and a dot vector to reside at static offsets from the frame pointer. M cannot be placed among the other local variables because it would prevent those higher in the frame from having static offsets. Additional variable size arrays or records are easily accommodated. So this is the elaboration time allocation of arrays in ADA or C99. This is array layouts. You can see continuous elements in figure 7.7. There is a column major and row major index. In column major A24 is followed by A34 It's only in Fortran. Reasons seem to be accommodate idiosyncrasies of IBM computer it was created on. Then row major, so 8 to 4 is followed by 8 to 5 in memory used by everybody else, makes array ABCD the same as array AB of array CD. So this is a row major index and column major index. In row major order, the elements of a row are continuous in memory. In column major order, thus each element is an 8-byte floating point number that the cache lines are 32 bytes long, and that the array begins at a cache line boundary. If the array is indexed from A00 to A99, then in the row major case elements A04 through A07 share a cache line. In the column major case elements A40 through A70 share a cache line. Layouts make a big difference for access speed. One trick in high performance computing is simply to set up your code to go in row major order. Example, for I equal to 1 to n, for j is equal to 1 to n, a is equal to value. Two layout strategies for arrays, that is continuous elements and row pointers. We can see figure in a slide. Row pointers are an option in C. Allow rows to be put anywhere. Nice for big arrays on machines with segmentation problems. Avoids multiplications, and it's nice for matrices whose rows are of different lengths. An array of strings, as an example, requires extra space for the pointers. So this you can see the continuous array location versus row pointers in C. So we can see that character day row pointer layout is an array of pointers to arrays. So the declaration of the left is a true two-dimensional array. The slashed boxes are null bytes. The shaded areas are holes. Declaration of the right is a ragged array of pointers to array of characters. In both cases, we have omitted bounds in the declaration that can be deduced from the size of the initializer. Both data structures permit individual characters to be accessed using double subscripts, but the memory layout and the corresponding address is quite different. Suppose we have a 3D array. Okay, so A of array we can declare like this, array L1 up to U1 of an array, L2 U2 of an array, L3 U3 of element type. So D1 is equal to U1 minus L1 plus 1, D2 is equal to U2 minus L2 plus 1, D3 is equal to U3 minus L3 plus 1. Let S3 is equal to size of item, then S2 is equal to D3 star S3 size of a row, S1 is equal to D2 into S2 size of a plane. Then calculating Aijk each time is address of A plus I minus L1 into S1 plus J minus L2 into S2 plus K minus L3 into S3. So this is a virtual location of an array with non-zero lower bounds. By computing the constant portions of an array index at a compile time, we effectively index into an array whose starting address is offset in memory but whose lower bounds are all 0. So we should compute all that at runtime, but we can make do with fewer subtractions. Here it can be given as it is equal to I into S1 plus J into S2 plus K into S3 minus address of A is equal to minus of L1 into S1 plus L2 into S2 plus L3 into S3. The stuff in square brackets is compile time constant that depends only on the type of A. So this is the static and dynamic portions of an array index. If ijk is known at compile time, then additional portions of the calculation of the address of aijk will move from dynamic to the static part of the formula as shown. So this is all about arrays. I will come with the next video, next class.